We are now being recorded. I'm going to open the webinar and start the live stream.
Thank you so much. So for your information, today is very busy day for the synthetic biologists. Especially we have 3 big events today. One is this one, and second one is we have the Central US Synthetic Biology Workshop. That is we kind of form an entire consortium only for the central, basically Wisconsin, Northwestern, all the way down to Texas. And then that happening actually right now. So unfortunately that overlaps. So I'm not sure how many people will be joining. And also starting your time 2 a.m. There are another big workshop that is about climate change and also the sustainability, I mean the road mapping. And I'm part of the council member and part of the road mapping member. So I need to attend that one after this talk.
I see.
So
that's by EBRC, right?
Yeah, EBRC, yes,
Yeah.
EBRC. So I'm basically council member, so I need to be there. And also I need to give a talk in the Central Synthetic Biology workshop. So to me, I mean, too many things going on today, but
three people's job at once.
Yeah, thank you. But this is my priority. This is my, the mission I need to do. I mean, so I love to start,
Very good.
So I'll give some, probably a couple of more minutes, because I mean, many people probably in Northwestern right now, because we have the in-person and hybrid kind of format. So I'm giving a talk, remotely, and then, but many people also attended there, and then they kind of start to talking because they open up probably 10 o'clock in the morning.
Okay.
My time. So that means midnight your time. And then the good thing is, I mean, we will record this one, and then YouTube, will, release a record, and then, kindly both of you, agree and then give a permission. And good thing is the first video we released around 10 days ago, and then we almost got, I don't know, I mean, I didn't check, I mean, recently, but we probably 1,000 views. So that's kind of, very good thing, I believe. And then probably more people kind of joining us, and then by, listening to that, YouTube. So I'm glad, I mean, and then even now, many people from Africa contact me saying how to watch the YouTube, and because the time zone is not great. And then Australia recently kind of found out this thing, and then they also kind of contact me. So I kind of exchanged so many emails, and then I kind of giving the YouTube, link coming to them. So this is huge impact, I mean, globally. I'm glad.
Excellent.
Okay, so I guess, I mean, we probably need to start. Okay, so good morning, afternoon, evening. Hola, hello, bonjour, ni hao, konnichiwa, 안녕하세요. And hello, everyone. Welcome and thank you for joining us, the 3rd seminar, and I call it Korean Northwestern University Day, because both speakers today are Northwestern University alums. Many people have asked how to pronounce the seminar series name, SynBYSS, SynBio Young Speaker Series. It's SynBYSS, not SynBYSS or something else. SynBY in Korean means mystery or miracle. So SynBYSS means multiple miracles. As a scientist and engineer, I did not believe in miracles. However, many miracles have happened to me since my miraculous recovery this year after many years of dying. This seminar series itself is also a miracle to me, thanks to the global excitement, making me exchange more than 2,500 emails in 8 weeks, but without feeling any fatigue, although I have been sleeping only 4 hours a day for more than 2 months right now. So I now believe in miracles. It is my absolute tremendous honor to introduce very briefly our pioneer speaker, Professor Sang-Yup Lee. Of course, there is no need to introduce him. He is Vice President of KAIST and National Academic Member, NAS and NAE, joining SynBYSS from Korea, midnight his time. I met him for the first time when I was just graduate student, actually second year graduate student, at an international conference where many of SynBYSS pioneers actually attended at that time, basically the 15 years ago. And he was the organizing chair at that time. I met many pioneers at that time, took pictures with them, even drank together, and started to realize my dream. He has been my role model since then, and I'm very proud of being Korean. So please welcome Professor Lee, and the virtual podium is all yours.
Thank you, Professor Moon, for very generous introduction. Good morning, good afternoon, good evening, everyone. My name is Sang-Yup Lee. I'm currently a distinguished professor at the Department of Chemical and Biomolecular Engineering, Korea Advanced Institute of Science and Technology, better known as KAIST. It is so nice to see you all through online. This COVID-19 situation is truly unfortunate, as it is preventing us from meeting face-to-face. But fortunately, we have Professor Tae-seok Moon, our organizer. So I want to thank Professor Moon, who worked tirelessly day and night to make this exciting event possible. Thank you, Professor Moon. Now, Professor Moon named today Korea-Northwestern University Day. So probably most of you know Northwestern University, as most of you seem to be in US. But Korea, let me very briefly introduce some Korean things. So as you might know, we have our own language, obviously Korean, and Korean syntax and words are completely different from English and other foreign languages. For example, in English, if you say, I am a boy, in Korean, you have to say, I, a boy, am. And because of this complete difference, I really had a hard time communicating when I first went to United States for my PhD study at Northwestern. And I was almost saying nothing for the first year because I couldn't. Well, it is fortunate that I learned English somehow, and I'm now talking in English. Also in Korea, we call last name first. So my name in Korea is pronounced as Lee Sang-yup instead of Sang-yup Lee. The Republic of Korea, that's a formal name of our country, or South Korea, has about 5,000-year-old history. It's a very long history. And the population of Republic of Korea is 52 million. GDP is about 1.65 trillion US dollars. And probably you are interested in this number, the annual R&D budget, that is about 83 billion US dollars, much smaller than US spending, but making it the 5th largest spender among the members of OECD countries. And also, that number, $83 billion, is about 5% of GDP. So percentage-wise, it's like a highest, probably the highest together with Israel. So today, having these great young scientists, it is my great honor to share some of my experience as a scientist and engineer at KAIST. So I want to start with what I did when I first became assistant professor at KAIST. So I was trying to find the unique problems I have to address that's different from my dear PhD supervisor who taught me so well. So I chose working on biodegradable polymers. And at the time I was starting up metabolic engineering because that's the time when metabolic engineering literally started. That's about 1991. So I started with bacteria and started to engineer. Now you can probably see that the first work we have been doing at the time was just cloning 1 or 2 genes, and hey, bravo, we did the metabolic engineering at the time. So time flies, and now the level of metabolic engineering empowered with even synthetic biology and systems biology is so enormous that it's just too complicated to describe in one paper. So you end up having probably 10 times a longer supplementary material, which most of you hate, and me too. And that's the current status of metabolic engineering and the synthetic biology. And then how do we select the projects or problems to solve? Obviously, you have to start with big problems. And the currently obvious big problems include not climate change. Climate change has been renamed as climate crisis already. And also human aging and healthcare issues, and also water, energy, and all these resource issues. These are the big problems. But as one person or a team of a few people cannot solve those big problems alone. So you have to break down into small important problems that constitute big problem, and then create ideas to solve those small important problems you have identified. And obviously, all of you who successful young scientists are doing that, but I just want to emphasize that, what Winston Churchill said. So success is going from failure to failure, because you are testing so many different creative ideas and you often encounter failures. But success is going from failure to failure without losing enthusiasm. So you have to continue, as Winston Churchill said. In Korea also, we have saying that motivation makes you start doing the work, because you identify the problem, you start working on it. But it is perseverance that makes you finish the work. So you never stop when you are tired. You stop when you are done. So that's sort of the philosophy of making things work. And that's sort of the theme of our lab, to finish the work to the end. And what we have been working on lately expanded from just establishing biorefinery. So we have been, as I said, I started my lab with the biodegradable polymer work, but I expanded it to sustainable chemicals, fuels, and materials. And we produced a number of different chemicals, non-natural chemicals, as well as natural chemicals. And then we are now expanding to those chemicals from nature that we can either eat or we can apply on our body. And this is going to be important because our resource situation might change due to the climate crisis. So it is great to join this important event today with you. And I'll be happy to listen to our heroine today, Dr. Chelsea Hu, whom I just learned that is capable of both wet work and in silico work. So she does both experiments and computation studies. And I look forward to listening to her great story. And thank you so much.
Oh, thank you so much. I mean, oh my goodness. I mean, that is so inspiring and touching. One, especially to me, and also I believe for entire global, community And I thank you so much, I mean, for a wonderful, inspiring talk today. Okay,
Thank you.
so yeah, thank you so much. I mean, this is absolutely my honor. So, okay, so now the main talk of today. I'm especially happy today because one of the originally scheduled young speakers, Ramiz Daniel from Technion, Israel Institute of Technology, is no longer eligible to speak. I mean, he was promoted with tenure right before the SynBYSS kickoff. So congrats. And I'm not sure, I mean, he will be here today, but this is absolute great start because our first SynBYSS alum to be tenured. So
Very
I guess,
nice.
I mean, this is, oh, go ahead.
Very nice.
Yeah, thank you so much. Yes, yeah. So great start of great tradition. And then I believe all the SynBYSS, alum will follow the same tradition down the road. So back to the Chelsea. So Chelsea, who is trained as both the theorist and an experimentalist to study the interdisciplinary field of synthetic biology, systems biology, and control theory. She currently works as a postdoctoral scholar in the Richard Murray Group at the California Institute of Technology. Her work focuses on feedback controls in synthetic biology with a hybrid approach of theory development, system identification, and experimental implementation. Chelsea studied chemical and biomolecular engineering at UCLA and earned her PhD at Cornell University in 2018. In her graduate study, she was advised by Professor Julius Love and Professor Jeffrey Warner to study dynamical modeling and system identification of RNA synthetic biomolecular networks. Personally, I love Julia's work, and then this is my absolute pleasure to have her as our third speaker and as a committee member and then chair. This is a very easy decision to have her as the third speaker today. So Chelsea, the podium is all yours.
Thank you, Dr. Moon. Thank you, Dr. Lee. It is my honor to talk about my work today. I will now try to share my screen. Actually, I can't share.
You should be able to share your screen.
I can only share the desktop. Is that normal?
Yeah, you got to switch the like we did earlier. Oh,
Sorry.
switch the view.
So we see your slide, and then you probably need to just change the view slideshow.
I don't. Okay.
We're still seeing presentation mode. There we are.
There we go.
How about now? All
Yeah,
right.
there we go. Thank you.
There we go. All right, thank you. Okay, hello everyone. My name is Chelsea Hu. I am a postdoc in the BPD division at Caltech, and I work in the Richard Murray Group. So I am a synthetic biologist, and I have been trained to do work as both an experimentalist and a theorist, as Dr. Moon just mentioned. Essentially, I want to understand how biological networks behave as a dynamical system, and how do we design them with robust and reliable dynamics. My work lies in the intersection of theory, simulation, and experimentation. So today, this is the outline. I will start with a brief intro about intersection of these three fields. and then I'll go provide some details with my projects as example. So the first one will cover most of my graduate work, where I developed a sequential system identification method to establish a modeling framework for RNA synthetic biology. And then I'll talk about my theory validation work in my postdoc training at Caltech, where I validated a key aspect of layer control theory experimentally. And then finally, I'll talk about how discrepancies between models and experimental observations throughout my projects led to discoveries and model development. Start with that. Synthetic biology has the potential to revolutionize technologies in many aspects. Nevertheless, a reliable synthetic biological tool we deploy should have reliable dynamics. So in general, this is what we want to do. We want to deploy the synthetic bug into an environment to perform sensing tasks. As it detects the signal, it will produce either therapeutics or enzyme or other chemicals as output to remedy the targeted situation. But when the signal weakens or disappears, the output should also respond accordingly. So this is actually pretty hard. I have been involved in iGen for many years, and one criticism about synthetic biology is always the safety and reliability. So people always ask, is it reliable? How safe is it? And how well can we control it? So to answer that question, we can draw some experience from other successes in engineering. So in 1903, the first aircraft was built, and to operate it, the operator had to lay on top of the aircraft. What it does is to do one job, is to control. He has to make a continuous adjustment in response to the change in wind speed and wind directions. At the time, the criticisms are very similar. Is it reliable? How safe is it? How well can we control it? We all know how that story progressed. Nowadays, air travels are even safer than road travels. The modern aircrafts have reliable and robust performance, but it's essentially built on the same foundation of the first Wright Flyer. The difference is that it has massive amount of dynamical controller modules designed and integrated into this system. So what are dynamical systems and feedback controls? So dynamical system is essentially a system whose behavior changes over time. So human is a dynamical system, living bacterial cell is, and also gene expression is a dynamical system as well. A control theory is a study on how to control these dynamical systems. And then the term feedback refers to a situation which two or more dynamical systems are connected together, and then the output of one system is interconnected to the input of another system, so the dynamics are coupled. And if we remove this feedback, and this is considered an open loop. So feedback controls is everywhere in our lives. The air conditioning system that turns itself on and off based on the difference between a real-time temperature and a set point temperature is operating based on feedback controls. Other examples, including the cruise control in your car and the blood sugar control in your human body, and the chemotaxis in bacterial cells. So how do we start to study control theory? Well, you start with a theory, usually is a qualitative understanding of a system. Like when you implement a negative feedback control into a system, it would normally speed up the system's response. And this is some understanding we have theoretically. And then you ask, is this theory going to hold in a certain situation? And that way you, to answer that, you describe the dynamical system with equations and then simulate whether if this theoretical scenario would hold. So this simulated result will also inform this theory and improve it. So this type of work is also called model development. So it's a major theme of systems biology, and many cancer metabolic networks are being studied this way. All right, now to get actual parameters in this model, we need to train the model with experimental data. So this part of the work is called system identification. Essentially, you identify the parts and how they will behave in this system and give it parameters so that the model is realistic and relevant to your experiments. The experiments here are not very interesting, but they can inform the model tremendously. And lastly, to have a theory validated, it needs to be experimentally confirmed. A lot of the founding work in synthetic biology fall into this category. So a validated theory can better drive model development and system ID work. Okay, let's take a closer look at these three types of interdisciplinary work. I believe you are familiar with these two works. These two papers published in 2000, they're widely thought to be the founding work of synthetic biology. So essentially, they took a theory on interconnected system and built it in biology to look for a qualitative confirmation. And from these type of works, we learned that bacteria can be programmed and utilized as mini computers. And then an entire field of synthetic biology rise from there. And after that, to get a quantitative understanding of a theory, a well-developed model is very important. So here we take this inducible expression of gene of interest as an example. So this set of DNA gets induced by the inducer X here, and then transcription happens, and it would make mRNA, and the mRNA was used to produce protein. So we can write a reduced model of just two species with production rate that's controlled by X in a Hill function, and a constant degradation rate, and constant translation rate, and a constant protein dilution rate. In the end, we care about this output P, and these are the unknown parameters left for us to identify. Or we can write another type of equation called chemical reaction network. So for short for CRN. Essentially, in this equation, you can write a lot more details in it. So the X inducer will bind to regulator, form complex bind to DNA, DNA binds to the RNA polymerase. You can go on and on. And in the end, we still care about the protein, and we got a lot more parameters involved and a lot more species. So the good thing about the CRN is it builds on fewer assumptions. So you're able to simulate them on a broad range of scenarios. It is very useful for complex natural networks simulation. However, because there's so many parameters involved, that it's very impossible for system ID. And also it's difficult for theory analysis and circuit design to use. Lastly, it's very computationally expensive. And the reduced model here has advantages that counters all of these, but the reduced model has its own problems. It's because it's built on more assumptions. So you can only simulate a limited amount of dynamical conditions. And also sometimes it could be missing very important details, and that is detrimental for a dynamical model. And no matter what type of model you use, in the end, you have to system identify them to get the parameters. So we take the same example here of the reduced model. Essentially, we can use two types of data to get these parameters. The left-hand side is a distributional data. Basically, you can get it from a flow cytometer. And the right-hand side is a plate reader data. So the distributional data captures the stochasticity in nature. You get a distribution of behaviors in a culture. But because you can only take a snapshot at a time, so you don't get a lot of dynamical information. And on the other hand, the dynamical trajectory give you more dynamical data because you can measure the culture over time. So the axis is time. but it does not capture the stochasticity because you're only measuring the average behavior of cells in a culture. Okay, so one thing I want to focus is the dynamical data. It is because it is a unique advantage of synthetic biology. We can use clear time frame and fluorescent proteins to get system dynamic outputs. And so these profiles are not available in natural systems. All right, so we covered the three of these fields. So are we there yet? Can we build a safe and reliable and controllable synthetic bug? Well, we need to fully integrate theory, simulation, and experimentation to get there. And this integration takes a path in the development of model development, system identification, and the theory validation. And today I'll tell you about my effort on integrating these three circles. Okay, first I'll tell you about my work in developing models and SysID methods to build model frameworks for small RNA circuits. I did my PhD with Professor Julius Lux at Cornell, and then we moved to Northwestern. The Lux Lab studies regulatory RNAs. This is a simple illustration of how antisense RNA repressor works. So if you have an attenuator sitting upstream of a gene of interest, when the antisense here is not present, the transcription is allowed to go through. But when antisense is present, it will interact with this attenuator and cause a conformational change. And so that this attenuator folds into a termination hairpin that would terminate the transcription so that the downstream gene is not going to get transcribed at all. Another component of my graduate study is TSTL. So TSTL is a cell-free system. It's composed of cell extract, buffer, energy mix, and a network DNA. There are many advantages of TSTL, but to my interest, it is a reduced and simplified system where some of the key assumptions in reduced models are true. So in this work, we used a RNA cascade. Here, when the first layer is present, it's just an attenuator and superphoto GFP. There's no repressor. So GFP will turn on, and this is the dynamical profile. And when you have the second layer present, and this repressor will repress the expression of GFP, so you have a repressed profile. When the third layer is present, it will repress the expression of the first repressor, so the system will turn back on. All right, so in the end, started with a small set of model, and we expanded to 8 equations and 13 parameters. 13 parameters is still quite a lot for a full identification. So we used a method called sensitivity analysis. So sensitivity analysis is an algorithm that analyzes your proposed experiment and tell you what parameters you can get out of it. Essentially, if I propose a simple experiment, say the first layer, and I'll ask the algorithms to just wiggle on every single parameters that are involved in the system and ask what parameters will cause the most drastic change on my measurable output. Here is GFP. And at each time point, it will do that. And in the window of 100 minutes, I end up getting these bars. So these bars that lit up shows the parameters, they're sensitive and identifiable if I supply this experiment result. And now I know that I can use this very simple experiment to define these 5 parameters. And I pass it to a more complicated design and say, you know what, these 5 are already identified, don't worry about it. Can we find the next most identifiable parameters with this experiment? And in the end, I got 3 more parameters. And I passed this on to the next one, and I got another 3. And in the end, I got all 13 of them. So I went, did all the experiments and used the experimental data to train the model. And in the end, we got all 13 parameters, and then the training fit was really good. But the ultimate test is not whether the training data is good. It is to use to train the model to predict new constructs and see if that prediction is correct. So here we simulated 6 new experiments with new DNA concentration, double attenuator, and also swapped parts with both 2 and 3 levels. Here now we use the model to predict the dynamic trajectory I should see with a 95% confidence interval. And this is what I end up getting experimentally, and then the prediction is spot on. And now we know this method works. So in the following project, we use the same parameterization method and modeling framework to design a small RNA-based auto-regulation. So with the model, we proposed 2 versions of the circuit. One is with a 1 copy of the repressor, and the other one was 2 copies. And the model seems to think that we need to use 2 copy to achieve enough dynamical separation and then response time speed up. And this was the predicted dynamics with the model. And when I did experiment, it was actually true. So finally, we implemented the design that the model predicted and a TSL prototyped into living cells. And then this is in living E. coli, and we can see this clear separation and the response time did speed up. All right, next I would like to talk about the work where we experimentally validated key aspect of layer control theory. This is what I did at Caltech. So layer control has been widely used in mechanical and electrical engineering as a optimization strategy. It is because it's theorized that the performance of any controller is bound by this trade-off between robustness and efficiency. Essentially, what it means is that if you have a controller that is very robust, it means it has to be inefficient. And if you have a controller that's very efficient, that means it is probably very fragile. And then to overcome that, you can layer the controllers together so that it will push the performance to this ideal corner of both robust and efficient. So it's widely used in engineering. So take an aircraft flying from LA to Boston as an example. A fast but fragile controller is used to react to the change in wind direction and wind speed in order to keep the aircraft stable in turbulence. But a stable but slow controller is also used to keep the aircraft on track to get to where it wants to go. So you will land in Boston instead of New York. In biology, we see layering and redundancy as a very common architecture style in biological systems. We see in neurological networks and a bacterial endogenous network. For instance, here we show on the right panel that in heat response, cells adopt 2 feedback loops and a feed-forward loop to regulate the heat shock response system. So why does biology use layering as a strategy? Well, it is a hypothesis that this trade-off limit between robustness and efficiency is universal. And the layering as an optimization strategy is also adopted by nature for the exact same reason. And we wonder if it's true. And we wonder if this could be the key to engineering robust synthetic biology. So to answer this question, we designed a node-based layer control architecture for analysis. So there are essentially 3 species in this design. There's A, B, and R. A would induce the production of B and its byproduct R. And R will regulate the output of the system B directly through this SynBYSS feedback directly on B. Or it will regulate the output of B indirectly by regulating its inducer A. So here on the right panel, there's a modified Bode plot that is converting the dynamics in time domain to a frequency domain. It is a very common tool for systems analysis. And it shows that with a disturbance of the same magnitude, the system output responds to the disturbance more drastically when the disturbance frequency is low. And as the frequency goes up, the response actually diminishes. So I understand this is very hard to explain. So I have this thing that this is how I learn it in class. So essentially, if this is a system, and the bottom of the iPod case is the output, and the input is my force that I supply from my hand. And if I use a low frequency disturbance, the output would change accordingly. But if I increase the frequency of the force, the placement of the iPod doesn't really change much anymore. So this is a demonstration. I hope that that makes sense. And here at the bottom, we did a 10 by 10 parameter space search for each of the design. So the parameters we search are binding affinity of the regulator and also the degradation rate of the regulator species. The 4 columns are open loop, SynBYSS feedback, trans feedback, and a layer feedback. And the first row is the disturbance magnitude, and the bottom row is settling time after the disturbance is being removed. So the gist of it is that on the top, if it's bluer, it means it's more resilient. And if it's bluer on the bottom panel, it means it's more efficient. So essentially, this shows that the SynBYSS feedback is more resilient but less efficient, and the trans feedback is more efficient but less resilient. And the layer feedback here, we see that inherits the both advantageous traits from the single layer controllers, so that it overcomes the trade-off. All right, so we want to design this and implement it in living cells. So the question is, does it matter if the regulator species is RNA or protein? So to answer that, there are actually, so 2 by 2 equals to 4 designs we need to look at. So there's RNA cis, protein trans, RNA trans, protein cis, RNA cis trans, protein cis trans. So we basically expanded the model to capture more detail and then simulate the trajectories of them. And I scaled them to the same equilibrium so we can look at them with a fair comparison. Here at equilibrium, I gave it a low frequency disturbance and held it for a while and removed it and watch everything to recover back to its equilibrium. And this profile for each simulation will give me information about how robust it is and how efficient it is for it to recover. So essentially we have 9 constructs, 9 designs. There are 4 layer feedback and 2 different SynBYSS feedback, 2 different trans feedback, and 1 open loop. So total of 9. And for each of them, we randomly generated 6 sets of parameters. So there are a total of 54 trajectories, and each dot of them is plotted in this trade-off plot. And you can see that all the purple dots, they're all layered feedbacks, and then they're all overcoming the trade-off and coming to this corner. And so in the end, we don't want to build all of them. We want to build one of them. So we picked this one that's the closest to this corner, and this is regulated by RNA via SynBYSS feedback and a protein via trans feedback. Okay, so now we want to build this in cell. And the goal is to compare the dynamics for open, trans, and layer and feedback loops. So we built all of these with the exact same context, with the mutated regulator pieces. So I'm going to skip the whole painful process of actually building it. And so we pretend that we have the result right away. The model dynamics we generated from the original model shows that at our 4 to 7, you essentially reach steady state, and then nothing changes after that. And when we measure the dynamics in cell, it looks more or less the same story, but that's only if you truncate the entire experiment and only look at the first 7 hours. Because if you look at the whole experiment for 16 hours, the dynamics looks like this now. So because cells are now growing into stationary phase, and their dynamics is naturally much more complex. And there will be no stationary phase in this case because there's no supplement of fresh media, and the cells will grow to capacity and start to die. All right, so to remedy that, we ran the experiment in 2 groups. So the intact group and the test group. So essentially the intact group will go through the mechanical wash and resuspension of media and all the steps, but only with one key difference, that is the targeted perturbation. So in this case, we grouped the 4 constructs to 7 hours, and we wash them and resuspend them in new media. And in the intact group, it goes into the same new media that we used for the first region. And for the test group, it's suspended in a media that does not have any inducers. So it's a wash. And then after that, the disturbance was removed and everything was resuspended to the recycled media that's prior to the disturbance. And we used the test group dynamics and subtracted by the intact group dynamics to get this unscaled dynamical deviation. And then also to want to look at a fair comparison, scaled everything by the value that's prior to disturbance. And this profile is what we use for the trade-off analysis. So we took the previous scaled deviation profile and then calculated the disturbance magnitude and the response time of each of the individual colonies and plotted them into this plot. And as you can see that the purple the purple dots here, they're closer to the ideal region and overcomes the trade-off of single layer controllers. And then we interrogated a system with 7 other different perturbations, and it showed that for each one of them, layer feedback always overcomes a trade-off and achieve the better dynamical performance. So all of the purple dots are closer to the corner. All right, so finally, I'd like to share the most exciting aspect of my work as a hybrid experimentalist and a theorist. And that is when the experimental observation does not match the model prediction. And I promise I'm not being sarcastic. So in the first project, when I started building the model, in the end, I got this very beautiful fit of experimental data and this simulation. It did not start that way. So at a very beginning, when I ran the experiment, there's some kind of upward bending. There's some delay here that I couldn't capture. And no matter how extensive the parameter search was, and it just wouldn't work. So we hypothesized that it could be due to a initiation delay of metabolic cycles in TXTL. So the TXTL has extract and a buffer, and then when you add them together and DNA all together, it looks like there's a 20-minute delay. So we just incubated the buffer and the extract for 20 minutes and then add a DNA. And then from then on, the dynamics look beautiful. And then so we continue to use that as a as part of the protocol. And when I added the second layer, and all of a sudden still doesn't work anymore, because if you can see it, there's like a slight bending of the the experimental trajectory. And it looks like the repression comes later, and it doesn't really make sense because RNAs are supposed to be transcribed really fast because they're really small. And turn out is because the folding of RNA actually has a delay, and that's something we didn't know. So in another project, when James Chappell, now a faculty at Rice, created small RNA activators, and they're stars. He saw that when stars are used as an intermediate species for activating cascade, so essentially you have a promoter activating stars and star activating the GFP. He showed that the dynamic range of these cascades actually amplified the dynamic range of the promoter. And that didn't really make sense because we did simulation and even analytical derivation. It just shows that it's impossible. It's not something that's possible with our current model. So there must be something wrong with the model. And then we looked at it. The model adopted a common assumption for effective modeling, which is assumes a constant degradation rate of all RNA species, which is mostly okay if you don't produce a whole lot of them. But now here, the analytical derivation showed that in order for the assumption in order for the amplification of dynamic range to be true, the degradation rates of a small RNA at on and off states has to be different. And then intuitively, this is very easy to understand. So at off state, the leaky expression of this promoter will transcribe a little bit of a small RNA here. So this is a star. And because of the fast degradation, it will degrade everything really fast, and so that you won't get any output signals. But when you have the inducer promoters, the inducer molecules around, you'll produce a massive amount of stars, and so it saturates the RNA degradation machineries in the cell, and so the stars are getting degraded a lot slower, so that it actually amplifies your signal at on state. To explain that, we added a mini CRN to relax the assumption on RNA degradation, and we're able to see that this is true. You can actually amplify it due to the oversaturation of RNA. So to further interrogate it, we used a sequestrator. So essentially, it is another piece of some small RNA that would disable stars. And the hypothesis is that if the sequestrator gets degraded a lot faster at off state, then you'll see a smaller drop at off state. The signal will drop quickly. But because it gets degraded a lot slower, so that its effect is stronger than at on state, you'll see a bigger drop here. And this is exactly what we saw in experiments. All right, finally, let's go back to the layer control model. So as I mentioned earlier, this lack of equilibrium is a major mismatch between experiment and model. And this is because normally we model the system with a constant degradation rate of protein. So degradation rate of proteins is dominated by cell divisions, and we usually assume it's a constant. But if we really look at the profile, this is dynamical data of cell growth, and then this is the growth rate. If you take a look at it, it was never a constant. It accelerates and then decelerates. So So I started working on a model that captures the entanglement of dynamics in two scales. So there's the populational scale and the molecular scale. So in this model, the production rate, degradation rates of synthetic species are now a function of growth. And this allows me to simulate a very similar profile that is compared to what I saw experimentally. Although there's still some details that are missing, and I'm still working on trying to system identify it to get all the parameters. But this caught my attention to the importance of multi-scale modeling for synthetic biology. All right, now let's wrap it up. In the future, I am still interested in working in these three intersections. And for model development, I want to look into the multi-scale models that links the gene expression and growth. And for system identification, I want to streamline system IID process with different types of data, like distributional data and the dynamical data. And for theory validation, I want to dive deeper into layer control and see how do we control multi-scale systems. But hopefully, eventually, we'll be able to merge these three circles and build our robust synthetic bug. All right. Thank you. Thank you, guys. Do you have questions?
Okay, so brilliant, Chelsea.
Thank you.
Actually, I love it. And thanks for your fantastic talk. And actually, I teach myself control theory and modeling as part of my SynBio course here. And in fact, for
great.
10th year this semester, and I should use your recorded video for my class, I mean, soon. So you did an excellent job, and actually covering the book Richard actually wrote, and I'm having using for many years. I love it. I love it. Thank you so much. So
Yeah, thank you.
Also I saw in the audience Professor Francis Arnold, and of course, I mean, Professor Sang-Yeop Lee stay until 1 a.m. his time, and this is absolutely wow. So any question? Anyone? So in that case, I guess, I mean, your talk is too difficult to understand because, you know, talking about
that was fantastic talk, Chelsea.
Thank you so much. I mean, staying up to now.
Yeah. So just one comment, which you don't have to follow because I think your work is already great, so you don't have to follow. But one additional request, I would say, is could you also think about the real application example where your modeling effort can be translated? Because, you know, most of us work with the money from a taxpayer's pocket, right? So it is great that you deliver great science. I think most public are happy. But under the situation of COVID-19 experience and also, experiencing the importance of rapid vaccine development and therapeutics, I think from time to time, you want to show that, hey, my science is mostly pursuing curiosity, advancing science, that's true. But I do have this important application which I contributed to. But that's again just an additional request. That's great.
Yeah, that's a very good point. That's a very good point. That's something I really have to think about for my job applications, because I think that's something I'm lacking. Thank you so much.
Yeah, that's absolutely the great point. Actually, that's actually related to my question. So this probably very difficult question for you, but I'll do it anyway. So so while waiting, I will start my question. So mathematics is very important for quantitative biology, as you know, and future of SynBio. And in fact, 20 years ago, it was so critical to start SynBio with 2 seminal papers by Jim Collins and Michael Eloyd, of course. And now, because of machine learning and AI, mathematics and computation and modeling are seeing their second wave, I think, in SynBio. So my question is, could you share your vision and perspectives on this trend and future? And you should think about it, but I don't expect your kind of correct answer today, but could you kind of share your thought?
Yeah. So the Murray Lab actually is trying to do AI on data and to use AI to develop models. But however, it requires way too much data. Like right now, with our capacity, with the amount of data we have, it's impossible. It requires millions of data for us to even train a small model. So I think a hybrid approach right now is for us to have these mechanistic model that if we have mechanisms that we are not sure of, we can put it in a black box and use AI to train that part. But the bigger framework still needs to be a mathematical framework that we traditionally use. Otherwise, the AI's lack of guidance and AI technology still is pretty early, and if we don't give it enough guidance, do we really trust the result? That's another question, right?
So excellent. So any question? And many of you kind of had headache because of we talking about mathematics, I guess. My daughter also had headache whenever I talk about mathematics to her. Well, I love mathematics, of course. Anyone?
Thanks.
Okay, so we already 11 in my time, and then 1 o'clock in Professor Lee's time. So probably we wrap up. So thanks all for attending. Despite we have another conference, Central Synthetic Biology Conference, happening right now actually, and then another workshop. That is the climate change or now crisis. After Sang-Yeom Lee kind of point out, and then we kind of making kind of draft for future roadmap. So I need to attend both of them to give a talk myself. So next week, we'll have another excellent and exciting, seminar with Caitlin Dean, Nature Chemical Biology editor, of course, and Teresa from UC Irvine. And then see you all next week at the same day and the same time as today. And we'll have the follow-up discussions shortly with the Zoom link shown in the chat box. I already shared that one. So if you have time and if you want to hang out with Chelsea, just please join. And then now we will use the Zoom, so you could kind of show your face and then your voice, and then see you in a minute. Thank you so much, and then see you next week.
Yeah, thank you.
Thank you so much.